Today, we're going to start with an application to your retirement. You could call this the most important application in Calculus 2 because it affects everybody. Of course, you might wonder, is Social Security going to be around when you retire in 50 years or so? Maybe in some form, but probably not as good as it's been for people in the past. It's probably not even going to be that great for me in 5, 10, 15 years. But hopefully, it's still there in some form. Probably the bigger part of your retirement is going to come from you investing money yourself into some kind of retirement account. And your money, will be invested in different things, bonds, stocks, that type of thing. And hopefully will grow to, you want to probably aim for at least $2 or $3 million by the time you retire. Now, when that happens, there is a danger. There is a danger that even if you save, say, $3 million by the time you retire, you could still run out of money before you die. That could happen, right? Medical expenses, cost of a nursing home, that kind of thing. You just don't have enough assets to cover everything that you need to pay for by the time you pass away. What you could do instead, I'm not saying this is a good idea, but what you could do instead is you could purchase, when you retire, what's called an annuity, which is essentially guaranteed income for life. You could take your pool of your retirement money, let's just pretend it's $3 million, and buy an annuity from some company, some financial company, that pays you a certain amount of money, say every month for the rest of your life, guaranteed until you die. Or you could probably even set it up until your spouse dies if you die first. So you cover your spouse too. There's downsides to that. One downside is you got to pay the annuity company money, fees to buy the annuity. You are purchasing the annuity. The other downside is they want to make money off of you. They're not doing it just out of the goodness of their own hearts. They want to make money off of you. So they're probably going to charge you more than what you could call the fair price, which would be what? It would be the present value of the annuity, according to some interest rate. It gets a bit more complicated than that because it really is not just the present value for you individually, because you don't know when you're going to die, but present value for lots of their customers, thousands of customers. So you need to bring probability and statistics into play. You need to think about things in terms of random variables and PDFs and CDFs for those random variables that you hope are good models. So pretend you've hit retirement age. You are 65. I'm probably not going to retire until I'm 70, which actually for me is like 14 years away now. You are 65, you're planning to retire, and you are wondering about purchasing an annuity. Let capital T be your remaining lifetime. Your remaining lifetime. What is life expectancy? Life expectancy is an average lifetime that is expected for a newborn baby. And for men, it's like, 78 years. And for women, it's like 82 years right now. That's gone up over time because of medical advances and better nutrition and that kind of thing. You might hope it's going to be higher when you are older. But in fact, if you make it to age 65, you are probably expected to live longer than the typical life expectancy because you've made it that far already. You might expect to live maybe another 20, maybe even 30 years on average. It is an average. Some people will die sooner. Some people will live longer. We need to model it with a probability density function. What is the PDF? What is the probability density function for your remaining life? Probably a realistic looking probability density function for the remaining lifetime. Might look like a normal curve to some degree, maybe a skewed normal curve, maybe something like this. That's not technically a normal curve because it's not symmetric. And I'm also not wanting it, I want it to be 0 when t is negative, so I don't want it to be truly a normal curve, but something kind of like that is maybe the best model for your remaining lifetime. Maybe this is 40, and if you made it to 40 years past 65, that means you made it to 105 years old. Maybe the mean is around, 25 or 30, something like that, maybe 25. If you make it 25 years past 65, then you make it to 90 years old. That's probably the most realistic kind of model for the PDF. However, it's difficult. Like, what is the formula for that? We do know formulas for PDFs and normal curves, but the downside of that is it's kind of complicated. And also, the CDF, cumulative distribution function for a normal curve, involves a non-elementary function, ERF. Remember ERF? Standing for the error function. So that sounds difficult. Sounds like we might want to try some simpler model. And we will do that here today. So this one's realistic. And the one we're going to do is not realistic, unrealistic. But it does have the benefit of being simpler, which we can actually do calculations for. Let's assume a triangular model like this, going out to 40 years past 65 years of age. And okay, I guess this would mean everybody has a kill switch in their bodies and they never make it past 105 years old. Of course, some people do make it past 105 years old. So it's not realistic that way. It's also not realistic in the fact that the density being so high near 40 means most people make it close to 40 more years, when that's probably not really true. Yeah, it's definitely not true. But it does have the benefit of having a simple formula, a linear function of t here. We want the area under it to equal 1. The area is 1/2 base times height, where I have an unknown height h. Set that equal to 1 because you want the total area under the PDF to equal 1. This implies 20h equals 1. So h is 1/20th, 0.05 for the height of that triangle. And what does that mean about the formula for this PDF here? It means the slope of that line, rise over run, is 1/20th divided by, the run is 40, is 1/800. And that means the formula for the PDF going through the origin is going to be t/800 when t is between 0 and 40. And technically 0 otherwise. That's understood. That is 0 otherwise. So there's our PDF. And as always, we want to use this to figure out the CDF. Capital F of t by integration. T squared over 800, or excuse me, over 1600, is going to be the CDF. That does satisfy the conditions of a CDF. In this case, since the variable can't be negative, it's 0 when t is 0. And when t is 40, it does equal 1. And it's up at 1 thereafter. Technically has a piecewise formula, but we're not bothering to write it down. This is the most useful part of the formula, you might say. All right, so there's our model for our remaining lifetime. How do we relate this to the annuity? Technically speaking, when you get an annuity, usually it comes to you like in monthly payments or maybe weekly payments. They pay you so much every week. It's actually, that's a discrete kind of payment system. It's actually harder to deal with that. That's what we want to deal with next week using series. It's trickier. What's easier is assuming it's a continuous payment stream. They're paying you money every second of every day for as long as you live. So we have to use the ideas from chapter 8 about present values of cash flows, income streams, to figure out the fair price. Because the fair price is going to be the present value. But again, not just for you, because again, you don't know what, you're just one person. You don't know when you're going to die. They don't know when you're going to die. But for all their customers, the fair price is going to be the mean of the present values for all their customers. So our cash flow needs to be specified. In this case, it's an income stream. To keep things simple, we'll assume it's constant. Though in reality, you would not want a constant income stream. You want it to go up over time because of inflation and maybe higher medical costs the older you get. So you would actually want an income stream that increases over time. If it was monthly payments, the monthly payments would increase. If it was a continuous income stream like this one, it would be the rate at which you're getting money every second of every day increases over time. And of course, you'd want it to be fairly large, hopefully like $100,000 a year. To make it so the numbers are not so big, let's use a smaller number. Say $1,000 per year. But this $1,000 per year is not individual payments of $1,000 once a year. It's coming to you every second of every day. How fast? $1,000 a year is about $2.74 a day, which is then about 11.4 cents an hour, which is about, well, 0.2 cents, 1/5 of 1 penny every minute. Yeah, not much. Yeah, every second it's that much. But just pretend, for the sake of argument, that's what's happening. If it were $100,000 a year instead of 1,000, you'd multiply it by 100. It's that many dollars every second, which comes to about 1 penny every 3 seconds. Not too bad. Okay, that's an income stream. It's not realistic that they would do that, but it's simple in terms of getting an answer that maybe is still a good approximation for what happened if they would give you discrete payments like once a month. Maybe it's still a good approximation. So this is what you get. And you get this how long? Until you die. Until time capital T. Now, again, you can set things up that if you die, maybe your spouse keeps getting more money after that point. But to keep it simple, let's just pretend you're single and you get this money until you die. What is the present value of this? It's somewhat traditional in actuarial science to call it capital Y instead of capital Z here. Capital Z we used for the present value of a one-time future payment at time capital T. Capital Y we're going to use for the present value of this continuous income stream that keeps giving you money until time capital T, giving you money every second of every day. Based on what we learned in chapter 8, this is an integral. It's an integral of the cash flow function, constant function of $1,000 per year in this case, but in more realistic situations, you'd want it to be an increasing function, having a graph that goes up over time, maybe a linearly increasing function. Keep it simple, we're using constant, times e to the negative interest rate times t. Interest rate is a decimal. On the homework, I've been saying use 5% interest, continuous interest. Here in class, we've been using 4%. So I'll use 4% again. It's not an indefinite integral, it's a definite integral from time 0 to time, well, capital T until the payments stop. Capital T is a random variable, an abstract idea representing the unknown time you have left to live once you've bought this annuity at age 65. But it really is applying to lots of people, thousands of people. It's a random variable. We use PDFs and CDFs to model its behavior, what values it tends to take on average, you might say. Therefore, capital Y is also a random variable. The fair price of the annuity is supposed to be the mean of Y. Whatever that mean is, that's our goal, is to figure out the mean of Y. In reality, keep in mind, the company that is selling you the annuity wants to make money. They're probably going to charge you more than the mean of Y. And that is to be expected. So I'm not saying that buying an annuity is necessarily a good idea. I'm just saying, if you do, you should want to figure out the mean of Y. Probably with a more realistic model, though, and you'd probably have to use technology. Oh, this formula involves an integral though. Oh, it's not too bad. We can do the integral. We can figure out another simpler formula for y in terms of capital T. If you do this integral, you could use substitution, let W be negative 0.04 T. If you do, then dW would be negative 0.04 dt. And dt would be 1 divided by negative 0.04. 1 divided by negative 0.04, negative 25. You effectively have to multiply 1,000 by negative 25 and get negative 25,000 e to the negative 0.04 t. Little t goes from 0 to capital T. You can always check this by differentiation, right? I'm using the fundamental theorem of calculus. The derivative of what I'm pointing at there, when I use the chain rule, I'd multiply negative 25,000 by negative 0.04. And if you do, you'll get positive 1,000. I'm going to skip a few steps. If you simplify this, you'll get 25,000 times, I'll put it in parentheses here, 1 minus e to the negative 0.04 times capital T, when little t gets replaced by capital T. Capital T is a random variable, capital Y is a random variable. Therefore, capital Y's got a distribution, a PDF and a CDF. Integrate the PDF to find probabilities. Use the CDF to compute the integral. Integrate the variable times the PDF to find the mean. Figure out where the CDF equals 0.5 to figure out the median. You can also figure out variances and standard deviations. We're not doing that. Use the CDF method. What is the CDF of capital Y? Call it just like last time, capital G. Now my variable is Y instead of Z, so I use a little y here. This is going to be an ordinary kind of function that you're always used to. It's defined using a probability symbol. It's the probability that the random variable, capital Y, is less than or equal to the given quantity, little y. Random variables are abstract ideas that are modeled by PDFs and CDFs. Random doesn't mean haphazard. There's patterns to things. And based on those patterns, you can figure out probabilities. You can write probability statements involving random variables. This is the way you do it. Takes some getting used to, but that's how it goes. Just like before, replace this new random variable with what it equals in terms of the old random variable. So replace capital Y with 25,000 times 1 minus e to the negative 0.04 times capital T. Keep the little y as is. You have to. I mean, this is going to be a function of little y in the end. And now, remember the goal. The goal is to try to use capital F, the CDF of capital T, to use this function. It is the probability that capital T is less than or equal to little t. So if I can isolate capital T by solving this inequality for capital T, that is what I want to do, to use that CDF. That's what we're doing. Divide both sides by 25,000 first, giving us this. Then I'll subtract 1 from both sides. Just doing some algebra here. These two steps don't change the direction of the inequality. Take the, okay, now before you take the log, divide both sides by -1s or multiply both sides by -1 to get rid of that negative sign on the left before you take the log. If I multiply both sides of an inequality by a negative number, I have to change the direction of the inequality. And then this times -1, I could just rearrange the quantities like this. In that last step, I just multiplied both sides of the inequality by -1. Now take the natural log to get rid of the e. Natural log is an increasing function, so you keep the inequality going the same direction. Almost done. Now divide both sides by negative 0.04, which is equivalent to multiplying both sides by negative 25. Either way you do it, it's a negative number, so the inequality changes back again to less than or equal to. And this is good because this is capital F of negative 25 ln of 1 minus y over 25,000. This is going to be what capital G of y is. I'm not quite done. I want to simplify this. I want to use the formula for capital F. Assuming the input is between 0 and 40, it's t squared over 1600. I want to use that. Assuming my input is between 0 and 40. So what am I going to get? I'm going to get capital G of y is this thing squared over 1600. That'll be 625 times this natural logarithm quantity squared. By the way, there's no property logs you can really use here to simplify that. I mean, you can subtract what's inside the parentheses and then use some properties of logs. But I think it's fine to leave it like this. And then it turns out 625 over 1600 is 25/64. And there is a reasonably simple form for the CDF of capital Y. If you're unsure about the 25/64, we can double check that. 625 over 1600 and 25 over 64 are the same thing. We should think about the domain. This is an area of math where thinking about domains is pretty important. Very important. There's some other areas of math where you're like, okay, do I really have to think about the domain? Is it really that important? And you can maybe get away with not thinking about it. But here you really have to, because it's going to give us the right region of integration where this formula is valid. So how do you think about the domain of this? The domain of this formula was t between 0 and 40. Y equals this function of t. The smallest value of capital T is 0 because that's the smallest value where this formula is valid. And when capital T is 0, well, it's the integral from 0 to 0. 0. Also, if you plug in capital T equals 0 there, e to the 0 is 1. 1 minus 1 is 0. That corresponds to dying right as you buy the annuity. So you pay the money, you die right away. Sorry, you don't get any money. The smallest y can be a 0. The biggest y could be is if you last as long as possible. According to this model, that would be 40 more years. If t is 40, what is the biggest y can be? 25,000 times, in parentheses, 1 minus e to the negative 0.04 times 40 power. The biggest that y can be is $19,952.59. That's the biggest present value you can get if you make it to 40 years after age 65. And most people are going to make it close. So the mean is going to be close, not too far away. It's going to be closer to this number than it is to 0. $19,952.59 if we approximate it. That is an approximation. In the homework problem I'm going to give you, I'll write the domain exactly involving E. This can be written in terms of E as well, but I'm not bothering to do that. this approximate. What's the PDF? Little g of y, as always, is the derivative of the CDF. So differentiate this. I'll need the chain rule. Bring down the 2 times 25 over 64 is 25 over 32. Then the ln gets raised to the first power, but don't forget the chain rule says to multiply this times the derivative of that thing. Derivative of log is 1 over the input, so I get this. But I need the chain rule again. I need to differentiate by the derivative of this thing, which will be negative 1 over 25,000. I can distribute this through the parentheses there, and it'll cancel with the 25,000 there. So one way to write the answer in the end is negative 25 ln of 1 minus y over 25,000 all over 32 times in parentheses 25,000 minus y. Once again, y going between 0 and 19,952.59. Okay, is this really right? Let's have Mathematica check it. Let's define capital G first. That was the 25 over 64 times log. Ln is log in Mathematica. 1 minus y over 25,000. That gets squared. Little g of y is defined to be the derivative of capital G of y. And we can look at its formula and maybe simplify it. Mathematica is writing it a little differently than me. It's switching around what you see on the bottom there, and by doing so, getting rid of the negative sign there. But it's the same thing. And this is a PDF. Is it decreasing, increasing? What does the graph look like? Over this domain, 19,952.59. Remember, most people are living a fairly long time, close to 40 more years. So most people get most of the money from the income stream. The present value should be fairly high. The distribution should be an increasing function. And it is. Does it really integrate to 1? We should probably check that. 0 to 19,952 point, again, what was it, 59? Little g of y dy, this should be 1. Yes? Amazing. It worked, I didn't make a mistake. What's the mean? The mean should be closer to 20,000 than it is to 0, because most people live a long time in this model, getting most of their money. Should be fairly large, 15,721. How about the median? This distribution is left skewed. Every once in a while, there's a very low outlier, somebody who doesn't live very long. Outliers affect the mean more than the median. The mean is going to be pulled to the left more than the median will. If I solve for where capital G is 0.5, I should get a bigger number than the mean. 16,935.2, ignore the negative 1. Mathematica gave me a little warning there, effectively saying, you know, solve does algebra, and maybe there are, maybe it can't be done, or maybe there are other solutions like what you see here. So in general, it's better to use find root with a capital F and a capital R. Though if you do use find root, you do have to give it a guess, like say 17,000, and you will get the right answer. We can also find probabilities. For example, what's the probability that your present value of a randomly chosen person is between 10,000 and 15,000? Integrate the PDF from 10,000 to 15,000, maybe get a numerical approximation like this. The probability is about 0.226. You could also use the CDF instead, because the CDF, this difference will be the same as the integral, fundamental theorem of calculus. And yeah, we can do other things too. We can find the variance and standard deviation too, but we're not doing it. So in the end, the quote unquote fair price of this annuity is 15,721.3. If the model for lifetimes is accurate, it's probably not. It's probably got too big of a mean. The mean should probably be less. People shouldn't live so long. And so the present value is probably smaller. The true fair price is probably smaller than this. But keep in mind that the insurance company or financial company wants to make money, and so they're going to charge you more than the present value anyway. And you have to decide whether it's still worth it for you to buy it. The benefit of keeping it is that you have that guaranteed income for life. You won't run out of money. The downside is you got to pay more. Maybe you don't get as much money every month as you want. That kind of thing. Those are the downsides.